Question 1 of this exercise says, without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. So we are going to use the theorems 1.5, 1.6 and 1.7 from the NCERT textbook, which when put together basically say that for any rational number p by q, when p by q is written in the lowest form, then p by q will have a terminating expansion. So this will have a terminating decimal expansion if q when prime factorized, the denominator when prime factorized, has only 2's and 5's. In other words, if q can be written in the form 2 to the power m, 5 to the power n, and it has no other prime factors, then p by q will have a terminating expansion, and p by q will have a non-terminating and repeating expansion if q is not of this form, which means basically that when q is prime factorized, then it has prime factors other than 2 and 5. So to summarize, what these theorems say is that if q has only 2's and 5's, so first you have to check whether p by q is in the lowest form, and once p by q is in the lowest form, then look at the prime factorized form of q. If q has only 2's and 5's, then p by q will have a terminating expansion, and if q has prime factors other than 2 and 5, then p by q will have a non-terminating recurring decimal expansion. Now let's take a moment and discuss why these theorems work. So the key idea behind why these theorems work is that when the prime factorized form of q in p by q has only 2's and 5's, then you can convert this into a power of 10, and you can rewrite p by q as an equivalent rational number where the denominator is a power of 10. For example, let's take the rational number 11 by 20. Now in this number, the denominator 20 has this prime factorized form 2 into 2 into 5. Now one pair of 2 and 5 make a 10, but the other 2 is alone. But if I multiply 20 by 5, so if I introduce another factor of 5, then the second pair will also get completed and I will make another 10. So this basically means that by multiplying 11 by 20 above and below by 5, I can convert this to an equivalent rational number, which is 55 by 100. And here I have converted the denominator into a power of 10. And this was only possible because 20 had only 2's and 5's in it. So now 55 by 100 can be easily written as a terminating decimal, which is 0.55. On the other hand, consider a number like 11 by 21. Now 21 has the decimal expansion, has the prime factorized form 3 times 7. So no matter what I multiply 21 with, I can never convert it into an exact power of 10. In other words, I can never write 11 by 21 as an equivalent rational number where the denominator is a power of 10. So this can never happen. So 11 by 21 will have a non-terminating repeating decimal expansion. So this is the basic idea behind these theorems that we will use to solve this question. So now let's apply these ideas to all the various numbers given to us. So the first number is 13 by 3125. Now if you prime factorize 3125, you will find that it has only 5's in it. So in fact, when you prime factorize the denominator, you can write this as 5 to the power 5. So this number 13 by 5 to the power 5 has a denominator which has only 5s in it. It has no other prime factors other than 2s and 5s. So this will have a terminating decimal expansion. So let's write it here. So the first number will have a terminating decimal expansion. Now let's take the second number. The second number is 17 by 8. And if I prime factorize the denominator 8, I can write it as 17 by 2 cube. So here also the denominator in this number, which is 2 cube, has no other prime factors other than 2s and 5s. In fact, it has only 2s in it. So the decimal expansion of this number will also be terminating. So let's write it here as well. So the decimal expansion of 17 by 8 will be terminating. Now let's take the third number. The third number is 64 by 455. Now 455 can be prime factorized as 5 into 7 into 13. Now this rational number, which is in its lowest form because there is no common factor between the numerator and the denominator. Now here the denominator has, in its prime factorized form, it has factors other than 2s and 5s. It has this 7, it has this 13. So the decimal expansion of this rational number will be non-terminating and recurring or repeating. So let's write it here. So the decimal expansion of 64 by 455 will be non-terminating and repeating. Now let's look at the next number. So the next number is 15 by 1600. Now let's write the denominator in its prime factorized form. So in its prime factorized form, the denominator has 6 factors of 2 and 2 factors of 5. So I can actually write this as 2 to the power 6 into 5 square. And if you want, you can actually pause the video for a minute and work out this prime factorization. So right now it's not in its lowest form because there is a common factor of 5 between the numerator and the denominator. So if we cancel that out, we'll have 3 in the numerator and we will have 2 to the power 6 into 5 in the denominator. Now in its lowest form, this number has a denominator which has only 2s and 5s in it, and it has no other prime factors. So the decimal expansion of this number will be terminating. So 15 by 1600 will have a terminating decimal expansion. Now let's go to the next number, which is in part 5. This number is 29 by 343. Now 343 is the cube of 7. So the prime factorized form of 343 is simply 7 cube. So now this number has a denominator which has prime factors other than 2s and 5s. So this will have a non-terminating repeating decimal expansion. So let's write it here, non-terminating and repeating. Now let's go to the next part. In the next part, the sixth part, the number is 23 by 2 cube into 5 square. So the denominator is already given to us in prime factorized form, and this number is in its lowest form, and we see that the denominator has only 2s and 5s in its prime factorized form. So this will have a terminating decimal expansion. So the sixth number has a terminating decimal expansion. Now let's go to the next number. So the next number, which is in part 7, is 129 by 2 square into 5 to the power 7 into 7 to the power 5. Now this number is in its lowest form because there is no common factor between the numerator and the denominator. The numerator is neither even, it's not a multiple of 5, it's not even a multiple of 7. So this number is in its lowest form, and in this form we see that the denominator has prime factors other than 2's and 5's. So it has this prime factor of 7 occurring in its prime factorized form, which means that its decimal expansion will be non-terminating and repeating. So this number has a non-terminating and repeating decimal expansion. Now let's go to the next number, which is part 8. Now in this part you will realize why it's important to look at the prime factorized form of the denominator when it is in its lowest form. So if I look at the prime factorized form of 15, this will be 3 into 5, and I see that because there is a factor of 3 in it, I could conclude that this number should have a non-terminating repeating expansion. But what we really need to do is to first reduce 6 by 15 to its lowest form. So 6 by 15 is actually 6 by 3 into 5, which is 2 by 5. And in this lowest form, the denominator has only 5 in it. It has no prime factors other than 2's and 5's. It has just 5 in it. So the decimal expansion of 6 by 15 will actually be terminating. So it will have a terminating decimal expansion. Now let's look at the next number, which is part 9, which is 35 by 50. So if you want, you can reduce it to the lowest form, which is 7 by 10. And 10 has only 2's and 5's in it. It is actually 2 into 5. So the decimal expansion of 7 by 10 will be terminating. So that's part 9. 35 by 50 has a terminating decimal expansion. Lastly, let's do part 10, which is, so let me write it here itself. So part 10 is 77 by 210, and I can write this as 77 by the prime factorized form of 210, which is 2 into 3 into 5 into 7. So if I cancel out the common factor of 7, I will have 11 in the numerator, and in the denominator I will have 2 into 3 into 5. So even after reducing it to the lowest form, 11 by 2 into 3 into 5, I see that the prime factorized form of the denominator has this prime factor of 3, which means that the decimal expansion of this number will be non-terminating and repeating. So 77 by 210 will have a non-terminating repeating decimal expansion. So with that, all the 10 parts of this question are done. To learn more about how QMath can help you crack school and board exams, explore QMath Leap, a live online classroom program run by highly experienced and committed teachers.